It's wonderful to be here virtually. This is a joint work with my collaborators David Gossett, Karen Morenz-Korol, and Mehdi Sulaimanifar. The plan of this talk is very simple. There are really two simple sections here. I'll introduce the problem, and I'll tell you how to solve the problem a little bit to some extent using low depth states. The talk might connect to some extent with this last part of Eric's talk where he discussed variational quantum algorithms and so on. So which are the buzzword these days. So there's a deeper connection here. The central object that I'll be considering in this talk are local Hamiltonians. I believe many of you may have seen this earlier many times, especially if you have some physics, background. But let me formalize it a little bit in more of a computer science language, because that's where much of the motivation comes from. And it's also possible that I'll also give some examples as we move forward, but I'll keep things slightly more abstract at this stage. So imagine a graph with a certain set of vertices V and some edges. And let's say the graph has a fixed degree D. It doesn't have to have fixed degree, but for convenience, we're going to assume that the degree is D. A Hamiltonian on this graph is simply, it's a very simple Hermitian matrix. Also, we imagine some qubits placed on each vertex. So if there were like a two-dimensional qubits on each vertex, then it's like a 2 to the 6th dimensional vector space here. And the Hamiltonian is basically a sum over Hermitian matrices, where each Hermitian matrix is indexed by an edge. So LK is an edge here. The property which makes it a local Hamiltonian is that each of this Hamiltonian HLK, each of the Hermitian matrix HLK, it only acts non-trivially on the qubits L and K. So for example, H12 will be certain matrix in the 4-dimensional vector space of 1, 2, and it will be an identity matrix everywhere else as a tensor product of identity matrix. So that's the picture that we have to keep in mind, roughly, that this matrix doesn't do anything on qubits other than L and K, and it does something non-trivial, something interesting to qubits LK. So you can think of this as an interaction between these qubits. In fact, much of the results in this talk also generalize to more than 2 local Hamiltonians, where we think about hypergraphs, like we think of vertices and edges now become subsets of vertices, but I'll skip that for convenience. It doesn't lead to anything conceptually interesting so far. So if we have a Hamiltonian H, we can, it's a Hermitian matrix, so it has a spectrum, and we can think of we can plot the spectrum from the lowest to the highest. The lowest energy is called the ground energy. That's something which people love to study a lot. It's basically, if your system is very, very cold, as in most of the quantum computers these days, you'd expect the system to lie in the ground energy. And then the energy goes all the way to max energy, which is extremely, extremely hot temperature. I don't think it exists in the world anymore, but you can think of lambda max as the max energy. So ground energy is something which people want to study a lot. That's something, so estimating ground energy is a very interesting problem. But for this talk, I'm just going to change things a little bit. I'm going to talk about max energy instead. It doesn't make a difference, because if I change H to minus H, then the ground energy becomes the max energy becomes the ground energy. So it doesn't make a difference, but it connects well with some of the classical computer science results. That's why I made this very potentially inconvenient and confusing change, but hopefully you can ask me questions and we can clarify if there are any confusion around this. So we'll be from this point, we'll be talking about trying to approximate the max energy of the Hamiltonian, which in the minus world is the ground energy. So a few results are very well known. In fact, these are some of the pivotal results of this topic. So it's known that if you want to approximate the max energy up to a very tiny error, which is 1 over number of edges to the power 2 or 3, something like that. In this case, this problem is extremely hard. It's known as QMA hard. QMA is a quantum version of NP. Problems in NP are already hard, and QMA makes it even worse. So this problem is going to be pretty difficult to solve. It was shown by Kitaev in a seminal result many years ago. In fact, many years before Kitaev's result, a little bit maybe around similar time, and another result was shown in the classical world, which is that if you have a classical Hamiltonian in which every local term Hij looks classical in some sense, I won't go into the details of what it means to be classical, then it's known that even if you want to approximate the ground and the max energy up to a large accuracy, which is you want some constant C, it could be a tiny constant, times the number of edges, which is a pretty large margin that you are interested in. Even in that case, it's pretty hard to approximate this energy. And that's known as the PCP theorem. So from practical point of view, NP hard is already quite hard. We don't know if quantum computers can help significantly in NP hard problems. Most likely they can't. So this is already a bottleneck for any nice algorithms that try to solve the problem of estimating the max energy. And we know that we can't expect to get a very good approximation. But then the point is that the world has to move on. I mean, these results are great. They're negative results, but we still have to keep pushing forward our techniques and algorithms. So one of the standard problems in this area, classical and quantum world, is that, well, how well can I really approximate this max energy? So can I efficiently find a number lambda given a Hamiltonian H, which someone has specified to me very properly? Given a Hamiltonian H, can I find a number lambda such that the ratio between lambda and the max energy, taken over all possible Hamiltonians that you're interested in, is as large as possible? So that's the goal, essentially. Like, we want the approximation ratio, which lambda over lambda max, this number has to be considered over all Hamiltonians to be fair. What's the best ratio I can imagine? So I'll give you some examples, and once I tell you some examples, I think some of the abstract concepts that I described might be more crystallized. So let's go over that. So one Hamiltonian is the Heisenberg interaction. It looks like this as a matrix. So Hij, it acts on qubits. It's like I minus poly x, y, and zz. That's a particular interaction. I'm assuming that people are familiar with these notions. But again, please interrupt. Feel free to interrupt if anything is confusing here. So if you write this down as a matrix, then this basically Hij projects onto the maximally entangled state between qubits I and j. So this is known as a Heisenberg interaction. And maximizing the energy amounts to trying to make every pair of qubit maximally entangled. We know that that's hard. We can't make every pair of qubits maximally entangled. That's known as monogamy of entanglement. So I can't achieve R to be very close to 1 so easily. But there is a series of results that have helped me progress on this problem. So, for example, the result of Gharibian and Perek from 2009, they gave a 0.498 approximation algorithm for this problem. That means they gave an algorithm which, on any instance, outputs a value lambda. It's efficient, and it achieves at least roughly half approximation ratio. So despite the fact that you don't know what lambda max is, you're guaranteed that your value is at least 0.498 equals 5. Later, we improved this result to 0.531 using a slightly more complicated states, and then Perek and Thompson improved this to 0.533. That's one example. More generally, if your local terms are positive semi-definite matrices, that's a very well-known study class of Hamiltonians. In this case, some results were obtained by these authors, and these authors showed that you could get a half approximation for any Hamiltonian, that's PSD, like this, but that approximation may not be efficient, but it will give you a nice product state, which I'll get into that soon. There are other examples as well. So, for example, if your local terms Hij are traceless, that means, oh, sorry, is there a question? Okay. So if the local terms are traceless, which means that there is no identity term in Hij, In that case, these authors gave a 1/9 approximation to the max energy. This, I believe, is also not efficient, but they show that you can find a state if you take some time and get some good result. Physicists might be interested in, physicists might object to my talk from the very beginning. They might say, hey, who cares about these graphs anyway? The world is 2-dimensional or 3-dimensional. And it makes sense to think of, for example, a planar graph or graphs that are living on a lattice or something like that, or 2D or 3D lattice. So whenever you have, for instance, a 2D or 3D lattice or 4D lattice, take your favorite, or if you have a planar graph, in this case, you can achieve an arbitrarily good approximation. Like for any epsilon you like, 0.00001, you can get a very, very good approximation by simply cutting the lattice into parts and solving each part. So that's well known. That's been around for a while. And also remarkably, the result of Brandau and Harrow from 2014, it showed that if your graph has a very, very high degree, that means the degree of the graph, if each qubit participates in many, many terms, in that case, you can put this problem in NP, which means that you can, not efficiently, but at least in NP, you can find a approximation ratio that's very close to 1. I'm being slightly vague here, but in case it rings a bell for anyone in the audience. So that's roughly the set of known results. I might have missed several results here, so apologies for that, but that's at least as far as I know. So one thing that happens in these results, and in fact, it's very natural. It's a very natural property to expect, which is that, well, these algorithms are in fact classical. That means these are all classical algorithms that give you, for a given Hamiltonian, they give you an NZ. And these classical algorithms output usually the most classical state out there, which is a product state. That means the state that they exhibit, which witnesses that your energy is at least R times max energy, R is approximation ratio. These states are of the form psi1 and psi2 and psi. Like these are single qubit product states acting on each qubit. But we know from our usual intuition that we don't expect product states to be the maximum energy states. Or if you're thinking about the ground energy world, then also we don't expect the product states to be the ground states. We expect the states to be highly entangled. So what happens is that these techniques in these works, they don't really get to such states. They always exhibit a product state that achieves a decent energy. So the main question that I believe has been a driving force, I'll motivate it a bit more in a few slides, but the main question has been that what kind of algorithm out there can really approach the space of highly entangled states, which we expect are the objects that really capture the complexity of max energy or ground energy. And in fact, the constraint is that I should be able to do it efficiently. I shouldn't take too long time. I mean, it's always possible to diagonalize the Hamiltonian, take 2 to the n time and get my answer, but that's too long. So efficiently, how can I go beyond the space of max energy states? So for that, so that's pretty much the introduction. I hope it made sense. And please feel free to interrupt. Also, I'm not sure if I'll be done with the talk too soon. There are some technical parts, and I'm happy to go over them more slowly. All right. So what I'll try to motivate here is that the next interesting class of states to go beyond the product states are states that are generated by low depth circuits, which I believe anyone who's working in variational quantum algorithms or QAOA would totally agree to. So let me tell you what a low depth quantum state is. In fact, I'm going to call it a trivial state for a not so trivial reason. Someone in the past called these trivial states from the point of view of topological order and so on, but actually these are very interesting. I don't think they're trivial at all. So I'll define a quantum state to be trivial, or maybe sometimes I'll call it a low depth, a constant depth, if the state can be generated in the following manner. You start with all zeros and you apply a constant depth circuit to all the qubits. So you have n qubits here, n equals 3 here, and you apply Hadamard gate, C0, whatever, phase gate, and so on. Whatever you want to apply it for a constant depth. So you don't have to, it's okay to apply it for a large size. That means you can add some ancillas if you want. That's totally fine. But the key point is that the total time of the computation should be constant. And that's a constant in the quantum state. So let's see why these are useful. There are a few reasons why we would like to work with constant depth quantum states. So first is that it's easy to identify a state like this. So for example, this includes product states. So if I start with all zeros and I just apply a single qubit unitary, then I obtain these states that are showed here, a product state, which that's easy to do. At the same time, even if I'm applying more complicated unitaries to the circuit, even in that case, these states are easy to specify because I can tell you exactly what gate was applied at each time, and that pretty much specifies the whole circuit, and hence it specifies the whole state. And if the depth is a constant, then you don't need too many gates to specify. So you just list all the unitaries in the circuit. That's easy to specify. It's also easy to generate from a specification. You simply start with all zeros, you apply these circuits, and hence you can also easily generate it if you have a tiny quantum computer in your backyard or something. Or if you're trying to use one of these big companies' quantum computer, then you can easily generate them without costing too much time. So so that's pretty good. So it's pretty good from the point of view of applications and the implementation and so on. Another nice thing about this is that from quantum complexity theory point of view, these states actually serve as a good witness in a QMA protocol. So maybe I should motivate this point a little bit more than I have done in this slide. And the thing is that, well, I mentioned long back in this in one of the early slides that the problem of deciding whether the max energy lambda max is some number or that number minus 1 over poly epsilon, poly E, that is a QMA complete problem as shown by Kitaev. What is QMA? QMA is a problem that looks like this. This is a Merlin sends a quantum state to Arthur. Arthur uses that quantum state to do a quantum computation and solve a problem. And then the Arthur solves the local Hamiltonian problem. So for example, Merlin could send the max energy eigenstate to Arthur. Arthur could do phase estimation and whatever to figure out what the energy is for a Hamiltonian, and Arthur would be convinced that indeed the energy is large or small. Now, the question is that, well, what if these states, like low depth states, actually were extremely good at capturing the max energy of a Hamiltonian? Then in that case, the Merlin doesn't have to send an arbitrary quantum state like a max energy state or a ground state. They can just send this circuit, which is a classical string. Arthur has a small quantum computer. Arthur can generate this quantum state, and then Arthur can measure the energy. So that kind of helps put some Hamiltonian problems into NP, where NP is the class of problems where you send a classical proof from Merlin to Arthur. So these states, like low depth states, are in fact extremely interesting from that point of view. From the point of view of trying to understand whether these can achieve, because they can serve as a good witness for QMA protocols. Okay, so that's some of the motivation for why one would be interested, and of course, I mean, as I mentioned earlier, that in variational quantum algorithms such as QAOA or VQE, these states are the central objects that people study, and arguably it's not easy to optimize over order n number of parameters, but that's fine because one can still take a reasonable amount of time compared to, for example, a random quantum state would require exponentially many parameters. So it'd be even more hard to optimize over it. And you might as well just diagonalize the Hamiltonian before doing something more complicated than this. So trivial states are also very useful in many of these recent algorithms that people have been interested in. So I'll tell you the main result of our paper, and what we basically show is that we give a general algorithm that can start with any product state, and that can improve the energy of the product state under some conditions. So the statement here looks slightly complicated, more complicated than what I would have hoped it to be. So let me go over it a little bit slowly. So again, let's recall the goal. The goal is to try to go beyond the space of product states. We want to be able to improve, get to better and better energies, but we want to leave the space of product states. We want to go to some more interesting states like trivial states or low depth quantum states. So the main theorem is that given a product state, there's an easy to compute. In fact, I'll show you soon how it looks like. There's a depth d+1 quantum circuit where d is the degree of the graph that I drew earlier. There's the degree of the interaction graph. This quantum circuit, and when I can apply this quantum circuit's u to the product state, and I get a state phi. The energy of the state phi with respect to your Hamiltonian is, well, it's clearly at least as good as psi if I choose u to be identity. But in this case, there is an improvement. And improvement is as follows. The improvement is that whenever this funny quantity called variance is large enough, d is the degree, I get a pretty large improvement in the energy. So it seems a bit strange why this quantity variance is coming in here. Variance roughly captures, so for example, if psi was an eigenstate of the Hamiltonian, the variance would be 0, because it's probably easy to see. And more generally, variance captures how far from being an eigenstate my state is. So one would expect that for most quantum Hamiltonians, variance would be large. And whenever the variance is large, we see an improvement. So let me say a few remarks about this. So typically, if you have a quantum Hamiltonian, the variance of a product state is usually, it scales as the number of edges, E. So this number over here is E square over E, so it scales proportional to E. So you actually achieve an extensive improvement. So your energy per edge increases that you expect. So your approximation ratio also increases. But then one could make a quick observation here that, well, this sounds wrong, because what if H is a classical Hamiltonian? In that case, the max energy eigenstate is a classical product state. There's no entanglement anywhere. So if I start with the best state that maximizes the energy of my classical Hamiltonian, there's no way I can make any improvement, because that is the best energy. I mean, there's nowhere to go beyond that. So this variance term exactly captures that. For classical Hamiltonian, the variance term is 0 for any product state. For the best product state, sorry, not any product state, because the best product state is an eigenstate of the Hamiltonian. So clearly, there is no improvement classically. So this theorem only works when my Hamiltonian is quantum. And when my Hamiltonian is classical, as expected, we cannot hope to say anything. There's no impossible to improve the energy at all. So that's the main theorem. The intuition behind the theorem is very quantum. So I'll spend some time trying to highlight where does the improvement come from. But let me tell you how the circuit looks like. So circuit is a very simple form. As I mentioned, it's a depth d+1 quantum circuit. So if d is a constant, it's pretty, it's a low depth, it's a trivial state. And we expect d to be constant in most interesting scenarios. The circuit is, it's a parameterized circuit. It's very similar to what you may have seen in QA or BQE literatures. And is defined as a tensor product of gates that act on edge by edge. So this gate acts on edge I and j. And it's basically a tiny time evolution or a rotation along this operator pi pj. So pi is a single qubit operator that acts on each side. And we specifically choose pi in the following form that we want. If we start with a product state psi, we choose pi to have 0 expectation with respect to psi. So for example, if psi was 0, 0, 0, 0, 0, pi could be poly x. So poly x on 0 gives me 0 expectation. I'll soon motivate why we do that. And the rough picture that we have in this case is the following. So here's what the circuit tries to do. So let's say, let's imagine a space in which let's imagine a edge, let's say edge 1 and 2. I is 1, j is 2. On the edge 1 and 2, my product state looks like psi 1, psi 2. Let's say it's a vector in certain direction. And let's imagine that the Hamiltonian H, it lives in certain other direction, not it doesn't align with this state, otherwise there's nothing to improve. Let's say it lies somewhere else. This circuit tries to find a way to rotate this state gently towards this Hamiltonian. And one would argue that why don't I just rotate it completely? Why should I rotate it gently towards the Hamiltonian? And the reason is basically the monogamy of entanglement, which is that if I try to improve the energy in a certain direction, if H is a quantum Hamiltonian, then I'm going to mess up the energy in other edges, simply because there is a tension between how much energy can be improved due to the fact that entanglement cannot be shared everywhere. So we have to kind of balance that. So we cannot completely rotate it towards this. We have to do a little bit, something slightly more care, and do it with a bit more care. So essentially, the picture that we have is that if we choose these theta ij's roughly to be a number theta of some order, then this rotation increases the energy by theta square, by order theta, sorry. So each edge gets a little bit of improvement because of this. But the monogamy effects kick in, and the monogamy effects decrease the energy instead of increasing it. And how much do they decrease? Well, here's a really bad scenario. Maybe they decrease by minus theta. So this increase and that decrease totally is useless. There's nothing to be gained. But the fact that we chose this P in this form, it ensures that all the first order terms, when I compute the expectation of u with psi, completely cancel. That means there is no first order decrease in energy because of this choice that we make. And the decrease only occurs in the second order terms. And the decrease is minus d theta square. So because each edge talks to d other edges, so there is a decrease of theta square for every other edge. So total decrease is d times theta square. So total increase is theta minus theta square, d theta square. And when you choose theta to be roughly 1 over d, you get a overall improvement. And indeed, you can see that the term here, there's a d square here for the regions, but roughly you see 1 over d sort of improvement in energy. So that's where the improvement comes from. This tension between these two quantities. So let me give you an example of, again, the Heisenberg anti-ferromagnet, in which case each Hij is basically a maximally entangled state. So Hij, it's a vector which is very entangled. You have a product state and you want to go towards it a little bit. So our result, in fact, generalizes this earlier result of a subset of us a while back. And there we showed that given a computation basis state, we could find a circuit which improved energy in this form. And it's the same picture that you see over here. And we can kind of subsume this. There's a 1 over d improvement here, although this is different from what you see in this picture, but there are ways to account for that by looking at variance more carefully. Anyway, so that's roughly the picture. And in fact, there's more to what I said. Product states are nice because they're the simplest states you start with. But in fact, there are other states out there. For example, ground states of local Hamiltonians, or for example, low depth states themselves. For these class of states, we can in fact still make some improvement. So what we can show is that if psi is the gapped ground state of some other Hamiltonian G, then there is a circuit which roughly is a time evolution e to the it, such that if I apply the circuit U, so that's U, this is U. If I apply U to my state psi to get phi, the energy improves. In a very similar manner, it improves as the variance of the state or psi with the Hamiltonian H over the number of edges, and this term L square, where L to the 10 is the locality of the Hamiltonian H. And this totally makes sense because if psi was, every state is a ground state of some Hamiltonian, but the Hamiltonian will be highly non-local, like n local. In that case, you don't expect any improvement. So in fact, it turns out that low depth states are themselves the ground states, unique ground states of constant local Hamiltonian. So we can in fact improve the low depth states as well. So what you can show through this is that you can actually improve the energy from product state, and then you can keep improving it to some extent. It doesn't go that far because the improvement decreases over time, but we expect that something better can be shown compared to what's shown over here. And in fact, for example, if you have a one-dimensional system, for example, if psi is the unique ground state of a one-dimensional Hamiltonian, then psi is an MPS. And what this result shows that you can also improve upon matrix product states, which may not achieve good energy, but you can get beyond that a little bit. Okay, so that's pretty much for my talk. Oh yeah, there's something more. Sorry. This time evolution runs for a constant time, and it's similar to a constant web circuit. Okay, so that's the overall. That's pretty much a set of results. There are several small results in the paper which I skipped at this moment, and the main question moving forward is how much improvement can I really see using these techniques? And in fact, these set of results try to motivate the usage of variational quantum algorithms. But how well can variational quantum algorithms really improve the energy of whatever we see? So for example, if this L to the 10 term wasn't here in this expression, this should show that you can improve the energy of a state, of a product state, improve all the way to max energy, as long as on the way you never got stuck in a local minimum. You never got stuck at a state which had like low variance, which is an eigenstate of the Hamiltonian. So that would be very nice for several reasons, not only from variation quantum algorithm reasons, but also from quantum complexity theory reasons. So one of the very interesting questions is this term L to the 10 really necessary? It might be necessary, but maybe there are some other conditions we can add to it, and we can keep improving the energy. So that's one thing. And in fact, let me tell you some of the potential results that would really be a major breakthrough in quantum complexity theory. So one would be that if you could achieve epsilon times the total number of energy, if you could achieve this kind of improvement in depth, any function of epsilon, any function that only depends on epsilon, then that would disprove a well-known conjecture, which is the quantum TCP conjecture. It has been open for more than 20 years now. And in fact, if you had a poly n in front of this, and you could achieve energy like this, then that would prove that QMA equals QCMA, which are two complex state classes that people believe aren't really the same. They don't know if they're the same or not. So improvements along this line are in fact fun to study for these reasons as well, and to bring surprises to quantum complexity community. I mentioned the NLDS conjecture, which sort of says that such an improvement is not possible. And in fact, it claims that this kind of improvement cannot happen forever. So we can't do it. We can't improve the energy forever because of this term. And in fact, the conjecture says that there are Hamiltonians out there for which there is an upper limit on how well can you increase the energy by order of seconds. So that's about it. And thanks for your attention. I hope I was not too below the time. What's the time right now? Oh, it's 12. Okay. I think we still have 30 minutes to go. Sorry.
Thank you. Thank you so much, Anurag.
No problem.
Are there any questions?
Yeah, or people can take the time and come up with a question. That's totally fine, because it's like 26 minutes to go for that. That's a decent target, I believe.
I have one small question. This L power 10, this power 10, what is there any intuition why the power 10 appears?
Oh, it's a numerical accident. I feel like if you worked hard enough, you'd get to 4, 3, something like that. But I feel like that term should really be much smaller than it's shown here. Maybe like something sublinear in L, maybe that'd be much more nicer. That would seem much more useful in comparison to what it says over here.
Okay, I have a question.
Mm-hmm.
Can you tell me how much does the if we have Hamiltonians defined on hypergraphs,
Mm-hmm.
how much does this this inequality is complicated by this?
Yeah, no, that's a very nice question. So if it's a k local Hamiltonian, if it's a hypergraph has k, if it's a k hypergraph, then as far as I remember, you get like k to the power something here, something similar. I think k to the 10, something small that comes up in the denominator over here. So which means that if the Hamiltonian is more non-local, that means if k is larger, the improvement is worse. which I'm not sure, I don't have an intuition for that, but that's what we get here. Yeah. So some dependence on k comes in the denominator, like, but a polynomial dependence.
Okay, thank you.
No problem.